very warm welcome to all our dear participants. Center of Excellence in Safety Engineering and Analytics, CoE-SEA, wholeheartedly welcomes all our dear participants to week 54 of the weekend talk on safety engineering, management and analytics. The event is conducted under Azadi Ka Amrit Mahotsav, which commemorates 75 years of India's independence. Today, we begin this event with this beautiful slogan, Asatoma Sadgamaya, Tamasoma Jyotirgamaya, Mrityoma Amritam Gamaya, praying to the Almighty to lead us from ignorance to truth, from darkness to light, and from death to immortality. Let me welcome our dignitaries onto the virtual dais. We have Professor J. Maiti, the chairman of the center, Professor O.B. Krishna, convener of the event, and Professor B.G. Menon, who is a professor of CoE-SEA and Department of Industrial and Systems Engineering, IIT Kharagpur, and our expert speaker for the day, Dr. Nicola Paltineri. He joined the Norwegian University of Science and Technology, NTNU, Norway, in 2016 and is a full professor of risk analysis since the beginning of 2022. In 2012, he earned his PhD in environmental safety and chemical engineering from the University of Bologna, where he is an adjunct professor as well. Between 2012 to 2016, he worked as a research scientist at the Department of Safety Research, SINTEF, Technology and Society, Norway. He serves as the associate editor of the journal Safety Science, and he is the leader of NTNU Energy Team Hydrogen and treasurer of the Society of Risk Analysis Europe. He serves as the Norwegian delegate of the Working Party on Loss Prevention and Safety Promotion within the European Federation of Chemical Engineering. CoE-SEA wholeheartedly welcome you to this event, sir, and we are very privileged to attend to. Now, I kindly invite Professor B.J. Menon to formally welcome our expert speaker. Over to you, sir.
Okay, thank you, Swin Josko. Good evening to you all. So today we are very lucky to have Dr. Nicola Paltineri, who is a professor of risk assessment in Norwegian University of Science and Technology, Norway. So today he will be delivering his expert lecture on the topic, Are Big Data Taking Industry Towards No-Brainer Safety Management? So this expert lecture on big data handling and management, I am very much sure will be of utmost importance to all our participants here and especially to the research scholars present here for today's lecture. So let me not waste further time without any further delay. On behalf of Center of Excellence in Safety Engineering and Analytics, so I welcome Professor Nicola to deliver his expert lecture this evening. So Professor Nicola, the dais is all yours. Sir, please.
Thank you very much for this kind introduction. As previously mentioned, we are talking about whether big data are going to take industry towards a no-brainer safety. I will explain a bit better what this statement means, what actually this question means. Let me see, yeah. Before, anyway, I would like to introduce myself, my team, and my university. Before I start talking about the state-of-the-art of data-driven approaches for safety management. And I give some representative examples of data-driven approaches, or better, as you have heard from my introduction, my background is in chemical engineering. So the idea is to give examples of practical applications of such advanced methodologies for chemical engineering purposes, okay? So I don't want to dig into the detail of the IT programming of such advanced techniques. Better, I would like to discuss their use and how their use can be performed, can be carried out by someone that is not that doesn't have an IT expertise per se, but is interested into using them as tools. Okay. I will then discuss the overall results from these examples and draw some conclusions. As I said, I would like to introduce myself. So let me see if I can also use the pen. So my name is Nicola Paltrinieri. I am a full professor of risk assessment, risk analysis. I teach the course of risk analysis. This is why I wrote risk analysis here, but risk assessment is actually more correct as the description of my overall topic. I sit in the Department of Mechanical and Industrial Engineering at the Norwegian University of Science and Technology in Trondheim, in Norway. And I'm also the leader of the NTNU Energy Team Hydrogen of the university, which is a team that is across faculties and departments and collects the experts on hydrogen-related topics. It's a team that is mostly focusing on providing the right support for the definition of future projects on hydrogen-related research. It is actually the largest cluster of R&D cluster in Scandinavia because we are quite many. If you consider professors, researchers, PhD students, postdocs, etc. However, I come from Italy. I mean, I was born in Italy, and I had my education from the University of Bologna, where I still keep a small position. I am adjunct professor over there, which means that I teach every year in autumn one small course at the University of Bologna. Well, this is just an overview of my research interest from both a basic and an applied point of view. From the point of view of basic research, I focus on the methodologies to perform risk analysis, and in particular advanced methodologies for risk analysis in order to catch more and more the evolution of risk, the change of risk, the change of risk that is reflecting the modification, the development, the evolutions of the system of our, for example, plant that might have some improvements because of maintenance, that might have some degradation because of material degradation. So we cannot really rely on a static assessment of risk made on day one for the following years if you have to take some safety critical decisions in the plant. You better rely on some methodologies that can take into account such evolutions of risk and some variations of risk. So this is basically my topic from a basic research point of view that has during the years developed towards more advanced techniques such as machine learning based techniques. And recently I have looked at meta-learning concepts, but I have to be honest that this is just a starting point, and I cannot say that I can fully grasp I can fully master the overall concept. Concerning the applied research, where do I apply these methods? Well, my background is chemical engineering, so I mostly focus on hazmat, hazardous materials, so hazardous substances. Here in Europe, we have specific regulations that are referring to the handling of hazardous substances. They are called Seveso regulations. So I'm very much focusing on these aspects in general that take into account how to deal with substances that have hazardous characteristics like flammability, toxicity, etc. And of course, when I moved to Norway in 2011, I started working with oil and gas because Norwegian economy is very much based on oil and gas. And this has been one of my main topics in the previous years, which is gradually, actually, at the moment, fading away to leave room to hydrogen safety. If, just to describe the current situation now in Norway, there is a lot of hype on hydrogen related technologies. I have quite a few projects on hydrogen safety because, of course, I deal with safety, I deal with risk analysis. And slowly, or not even that slowly, the topic of hydrogen safety is substituting the application area of oil and gas, at least in my research. I've recently spent 2 months at Kyoto University as a visiting professor, where I actually also focused on NATEC events, natural hazards triggering technological disaster events, which is just a starting point for future research on it. My team. This is me at the top of the pyramid. We are looking for an associate professor that can hopefully join my team. I have with me a very good postdoc, very promising postdoc that has won some awards as well recently, and a researcher who is actually part-time because she is also working as a researcher in a research institute here in Norway called SINTEF. Then I have 4 running PhDs, these 4 plus 2 PhDs that are starting in these weeks, in this month. They are all connected to various projects financed mostly by the Norwegian Research Council, so they are mostly financed on a national level. I have an exception for of a European project that is actually financing a new postdoc that is yet to come, but I will announce the position soon. My main university, because as I said, I have 2 positions, one in Norway and one in Italy, but the main position is in Norway, where I am full professor, permanent. So I can consider my university NTNU, the Norwegian University of Science and Technology, which is, of course, located in Norway, and in particular in 3 sites in Norway: Trondheim, Ålesund, and Gjøvik. The main site is Trondheim, where I sit. Then we have offices in Brussels and offices in Tokyo. It's a university that has a main profile in science and technology. It's the largest university in Norway. It's the most important university for engineering. Okay. But then, of course, there are also faculties on humanities, social sciences, medicine. Medicine is actually very important. We got a Nobel Prize in the medicine faculty 8 years ago, and other faculties. And we have 8 faculties. 55 departments. Now in 2020, so 2 years ago, we had 42,000 students. That, I guess, for you is probably not a big number, but for Norway is a big number, because Norway in total counts 5 million of inhabitants. Okay, so there are not many people living in Norway, and a university with 42,000 students is a big university. And this is the start of actually my lecture, my speech, which starts from these two pictures, these two faces. They are two people from the 90s, and they would like to indicate the fact that we have had different waves of interest in artificial intelligence. And one of these waves started in the 90s. And for example, some of you might remember AI, the movie by Steven Spielberg, which was actually the beginning of 2000. But anyway, it was towards the end of this wave of interest on artificial intelligence, where there were a lot of promises. There was a lot of optimism about the capabilities of these advanced techniques could have in many fields. And Professor Dickman in 1992 had a lot of hope in the fact that artificial intelligence and related techniques would help risk analysis, would make risk analysis way more advanced and way more dynamic, using these artificial cognition based science. On the other hand, you might know or remember that still in the 90s, Kasparov, the chess master, the Russian chess master, number one at the time, lost against Deep Blue, which was this artificial intelligence computer designed to play chess. Kasparov, after losing, okay, maybe he was a bit bitter because of the lost game, but after losing, he stated that this was not artificial intelligence. We couldn't talk about, we couldn't really say that this was artificial intelligence, because he had lost against a programmable alarm clock. It was the equivalent of a programmable alarm clock. So not really a piece of intelligence, but better something that was programmed to choose and put in practice the correct chess action. Okay. But was not more complex than that. So it was not really an example of intelligence. So the question for this lecture is, today, after 30 years, are we either on the side of Professor Dickman? So are we really meeting the promises that Professor Dickman stated, hoped for, or we are still in the situation of a programmable alarm clock, as Kasparov, the chess master, stated in the 90s? But we should first define artificial intelligence and clearly say what can be used and applied in the field of risk analysis, risk assessment. So artificial intelligence is intelligence that is demonstrated by machines, as I say here. And in particular, there are many subfields of artificial intelligence. Now, in this presentation, in my perspective, we are particularly focusing on machine learning. So artificial cognition, the process of learning by machine, that might be useful for the evaluation of risk in an industrial system, for example. And if we look at how industry is evolving, we see that it is developing, it is progressing towards this direction of exploitation of big data coming from several sources in industry. Just to give you an example, there has been many projects here in Norway, for example, in the oil and gas sector, about the monitoring of deviations of safety barriers, of specific safety process indicators that can be from the temperature and the pressure of our process to the attendance to maintenance training or the performance of correct inspection, etc. So it can be either technical indicator or operational indicator that together may give us a hint, a detail, an element, a piece of information of what is the overall risk of our system. And once again, I'm mentioning the regulations that we have in Europe concerning the handling of hazardous substances, and in particular the Seveso 3 regulation, because it's the third generation of this regulation. That is a regulation that has been defined on a European level by the European Parliament and then implemented by the different countries with some slight differences, okay? With this table, I just want to show that these countries have different approaches of, for example, dealing with the collection of past accident events or near misses of or releases of hazardous substances. A good example is given by the UK, that is not part of the European Union anymore, but it used to. They have the reader database and the process safety indicators that are describing the safety performance of a system that is handling hazardous substances. They are required by the competent authorities. So there is a collection of process safety indicators. There is a collection of these pieces of information. In France, we have an equivalent database that is pretty well structured and performed, and is also accessible, publicly accessible, ARIA or ARIA. But they don't have anything specifically mentioned in the decree for what concerns the collection of indicators. There is instead the main research institute addressing these aspects in a RIS that is calling for such a system. Italy has a system to report to the competent authority past events of deviations, accidents, and so on, but also is mentioning in the decree that there is a need for monitoring the safety performance indicators. While Norway is a bit more like France, where the past events are collected, but there is not really a system to monitor the process safety indicators. Instead, the main research institute here, SINTEF, is asking for such a system. So you see that the situation across Europe is aligned, even if there is not a systematic collection of such pieces of information that is described, that is mentioned, that is addressed by the regulation. But everywhere, or at least in these countries that I mentioned, there is a recognized need requirement for such information for the monitoring of such information that would help to proxy evaluate the safety level and so the risk. So to repeat the question at this point, is this database approach, this database perspective, going to effectively fully automate safety management? So are we gonna go towards this no-brainer situation where the computer will fully manage safety, fully assess risk and manage safety without the need of the human, of the operator, because we have artificial intelligence that will take over? Are we there yet? Is this something that is feasible at the moment? I'm not going to give the answer now, but anyway, I'm going to give a perspective from a process safety engineer, chemical engineer, process safety engineer, which is me. So I want to start with the concept within this topic, within this field, the concept of no free lunch, of the no free lunch theorem, the fact that there is not such a thing as a free lunch. In other words, we don't have an optimum machine learning method, and we have to consider the situation case by case, so these applications case by case. So for this reason, I also give three examples, three cases with some differences in order to show how these advanced approaches work and how they might not work. First example, prediction of the consequences of a hazardous substance release. So once again, we are in the field of releases of hazardous substances because of the overall application area of chemical engineering. And in particular, we want to know how to predict the consequences in case there is a release of hazardous substance, and whether we can do that with an advanced technique of machine learning, artificial intelligence more generically. What we did with my group, with my team, was to analyze the MIDAS database, okay, which is a pretty good database in my opinion. It's the database on major hazard incident database is the acronym that was used in the UK by HSE, Health and Safety Executive, until mid-90s. Okay, it's a database that has been stopped. I think it has now is part of the Reader database, but I don't have. I'm not fully sure about that. I'm just guessing. The MIDAS database is good because, in my opinion, okay, there are many events collected. There are almost 9,000 events, which are very clearly recorded using a specific taxonomy that help further analysis and help, for example, the studies that we have carried out based on machine learning approaches. How did we do that? Well, we considered the features of each event. And as I said before, we wanted to predict the consequence of each release event. So based on the specific features that are described by taxonomy, by specific terms from this clear taxonomy. We trained the computer, the machine, to identify the label, so identify the consequence class that might occur from a specific type of release. Okay, we are talking about then supervised learning. We are talking about classification, a classification approach. Okay, for of machine learning. This is instead the second example that I will discuss. We are going directly to the second example because I will show the results all together. An overall discussion is needed. We cannot really go into the detail of each result, but we can just discuss them in comparison to each other. Said that, this is the second example, an example that is more related to the oil and gas sector. It comes from my experience in the oil and gas sector here in Norway, where we consider the case of drilling unit, a semi-submersible drilling unit that is drilling in the North Sea. Actually, is a real example. And it's a floating drilling unit, so it's not gravity based. For this reason, it has to maintain a position that is on top of the wellhead where it is drilling. So you see, this is the drilling unit, and this is the wellhead. And of course, there are many factors that might push the drilling unit, the drilling rig, out of position. For example, you see that in this representation, it goes towards the right-hand side. And moving out of the position would mean tensioning the riser and would probably mean damaging the wellhead here, okay? Because of course the riser is not that flexible or extendable. There are some limits that we cannot pass for what concerns the position of the riser, and you see them as dotted lines here: the green, the yellow, and the red limit, and then there are also physical limits over after which we have a permanent damage to the riser, to the wellhead, and even to the drilling rig, because the riser would most probably impact here the pontoons, the structure of the rig. And what did we do here? In this case, we worked with synthetic data. There was a previous work on the definition of a big set of indicators, a large set of indicators describing many aspects that might influence risk of a specific drilling unit. We calculated how these indicators might affect risk, or at least we consider these indicators as features in order to predict the label, which is basically whether there is an increase of risk. So we are still talking about the classification. So the label is zero, is either 0 or 1. Whether there is an increase, we would have a label equal to 1, or there is a decrease, we would have a label equal to 0. Okay. Now, the original data, as I said, they are synthetic data that were obtained by complex work of modeling through logic trees and other techniques for risk modeling, coming from advanced indicator-based approaches, which are, however, too complex and too sophisticated, too difficult for an actual application in industry. If you present such a complicated, structured, deep analysis to an oil and gas company, most of the time they would say interesting, but they wouldn't really bother to put it into practice, given the time effort that is required. So the idea here is to bypass such refined, such complex modeling by feeding the machine with indicators, process safety indicators, and letting the machine predict the risk trend, whether the risk is increasing or decreasing. So in this way, we would be able to give a good support for safety-related decision making. And finally, the third example. This one was focusing on a large alarm database coming from an ammonia production plant, where there were some cases of power outage. In those cases, as you may guess or may know, all the alarms go off and give a signal the operator in the control room operator. The problem is that we have a power outage, and such a flood of alarms would be very challenging to deal with. Okay, the operator would need a way to filter, and there are already available filters in the field. Actually, would need a way to filter such alarms. I said that there are already available filters. So what is the novelty in here? Well, we are trying to. We have actually already published the work. We have suggested a way to dynamically filter these alarms, because the conditions change all the time in a system, in a plant, and the current tools that are available for alarm management are filters that are static, that you set at the beginning, but they don't take into account the different situation, the different conditions in which the plant might be. So the idea here is based on the features, so the characteristics of the alarm. Can we predict whether in the next hour the alarm will be chattering? What does it mean, chattering? It means that it's going to be an alarm that is going to pop up many times with a high frequency, which will mainly lead to a noise into the overall situation than giving a real information. Okay, so the prediction here is whether in the next hour the alarm will be chattering. So you may understand that this hour window is moving, because of course is the hour, the next hour from now, and in 10 minutes it will be the next hour from that moment in 10 minutes. So we are trying to achieve a dynamic evaluation of such chattering alarms, so a dynamic way to filter out those alarms. And this is the overall approach used to achieve such predictions, such machine learning classification models. The idea is to feed the machine, the computer, with part of the data set that we have available. So a part of the database that we have available. So it's the training data set where the computer will learn to associate the features with labels, with predictions. And then at the end, there is a remaining part that is used to evaluate the model that you have obtained from the training. So you feed just the features to the machine, and you compare whether the machine has predicted the correct label with the real label. And what did we use? We used two different approaches that can both fall under the umbrella of machine learning. But of course, if you are talking about multilinear regression, the first approach on the left, we mostly think of a statistical analysis. Okay. If you talk about deep neural network, then you are talking about more sophisticated approaches. Now, I have to give I have to say from the very beginning that when we talk about deep neural network, we talk about a specific an application of deep neural network based on a publication by some Google experts, because we have used the Google platform for this. And we have used, so for example, the parameters that were suggested, which means that the results we obtained could be improved, because we haven't done any optimization on those parameters. Okay. And I must introduce an important element in terms of parameters, though, that is discussed later in the results, is the threshold of the decision, let's say, probability, or better, the decision threshold that is expressed in terms of probability. Now, by default, is 0.5. What does it mean? It means that the model that is obtained by these machine learning approaches does not actually give us a result in classification terms, but it gives a result in probability terms. It says, yes, this event has this probability to be in that class. Okay. If we have a threshold of 0.5, then if the probability is higher than 0.5, the event will definitely be in that class. So at least the decision will be taken accordingly. If the probability is lower, 0.3, for example, then the model will say that the event is not in the class. Okay. So remember this threshold, because it's important and it might be useful in the application of these techniques. And now let's get to the metrics that we used for these three cases. And of course, I have to introduce what we are talking about. We have to introduce the fact that we are doing predictions. And of course, we are predicting whether an event belongs to a class or doesn't belong to a class. So there are positive predictions. The event is predicted to belong to a class. And there are negatives predictions, So the model predicts that an event does not belong to a class. If you remember, the results of the model are compared to the real data, which means that we compare the prediction with what it is actually in the reality. So if a positive prediction is positive also in reality, we have a true positive. If a positive prediction instead is wrong, and in reality is not a positive event, then we would have a false positive. Accordingly, we would have also false negatives when we are predicting negative, but in reality is not. And we would have true negatives when we are predicting negative, and in reality, it is actually negative. And now, first metric that is one of the most common and, let's say, direct, I don't know, understandable, the accuracy. So we are assessing how often the model classifies correctly an event, okay? So how often the model says, this is positive, and it is actually positive. This is negative, and it is actually negative, okay? It's a ratio between the correctly classified data and the total amount of classifications. Precision. What is the proportion of the positive predictions, okay, that was actually positive in reality, okay? And this is important. This is actually pretty important for safety management, the recall, okay? In particular, for the handling of hazardous substances where we really want to prevent major accidents, okay? What are the major accidents? Events that are that have low probability but very high impact, very high consequences, okay? There are many names describing these events, different characteristics, of course. The low probability, high consequence event described by Hans Passmann. There are atypical events that were described by me in one of my publications. There are, I don't know, the black swans even. There are many other names, the perfect storms, etc. So how do we catch the correct prediction of these events that have low probability, so low frequency, but very high impact? So we better predict them, okay? Because if we miss even one of them, it would be a big problem. Well, we should evaluate our model based on the recall, which is the proportion of actual positives that was predicted correctly, okay? So I want to know how many of these actual positives were actually predicted by the model. I don't want to miss them. So if then I don't want to miss these, if then I don't want to miss them, I want to have a high recall metric. And finally, we have the area under the curve of the precision recall, which is this is the curve of the precision recall curve, which is a curve that is plotted by changing the decision threshold that I showed you earlier. So if you change the decision threshold from 0 to 1, you will be able to plot several points on this precision recall diagram that will allow you to plot a curve, and the area under the curve is a good indicator. A good indicator of what? Well, if you don't get good results, or at least the results that you were hoping for in terms of precision or recall, you might look at this area under the curve and you might understand whether there is some potential for improving the model a posteriori, so improving the model after you have developed the model by variating the decision threshold. Okay, so by moving either in this direction or in this direction in order to improve the value of precision or recall. Now that you know the metrics used, we can look at the results. Okay, here there is a bunch of numbers. On the left of the table, you see the metrics that I just introduced. Here you see these titles that are showing the two different approaches that we have used. And this indicates the case that is analyzed. So when we are talking about C is the consequence class, and in particular is the prediction of a consequence class that has no fatalities, fatalities between 1 and 10, fatalities between 10 and 100. WDF is the wellhead damage frequency, yes. So it's the second case study. And this is the alarm that is chattering, okay? So this is the third case study. So you see these predictions have been carried out through these two different approaches, and then the models that were obtained were evaluated based on the metrics here on the left. And first we look at the comparison between these two different approaches, multilinear regression, so relatively simple approach, and deep neural network, more sophisticated one. And when you see green, it means that the approach is better than the other. When you see red, of course, is the other way around. You can see, probably you can spot that there is a bit more green on this side of the multilinear regression. Well, what does it mean? It means that there is not such a thing as a free lunch. It means that there is not a model that is good for everything, and a more sophisticated model like a deep neural network is not always working well. I have to say that, as I said at the beginning, we didn't really optimize all the parameters of the deep neural network. There is still room for improvement, okay? But the deep neural network approach is also very sensitive to the quality of data in input, okay? And there might be some cases, for example, the case of the database, the MIDAS database, that might not have fully reliable data in input because the database originally is made by humans, operators that have filled up the database once the event has occurred, okay? So there are some maybe mistakes, problems, issues, relative uncertainties that might be registered and felt and considered by the training for a deep neural network model. And for this reason, a more approximated multilinear regression might lead to better results. This is what I was telling you earlier, that we shouldn't look only at the accuracy, because accuracy might lead us to the wrong direction if we are thinking of if we are thinking of predicting, for example, major accidents that have a very low frequency, fortunately, very low probability, so they are rare events. An example is given if by this case, events that have a consequence of fatalities between 10 and 100. They are, let's say, the 1% in the database that we have analyzed. And in fact, if we look at the accuracy and if we look at the model that has been produced, the model says that 99% of the times, or at least the accuracy is 0.99. But if the model says that these events never happen, it will be right 99% of the times, which means that we are really losing this 1% that is meant to be predicted because it's the major event, is the rare event that we really want to be caught and considered and predicted for to prepare and to be able to prevent it. Okay. So we should probably look at the recall and trying to understand how to optimize the recall. So if we saw that the recall is low, we probably would need an approach that is leading us to an increase of recall. And a way to do that would be to optimize the decision threshold that I showed you earlier. On the other hand, if we are talking about events that have a higher frequency, so that are not rare events, and have a relatively low impact, it would be probably good to optimize the value of precision. We have different approaches for this. Once again, we can optimize the decision threshold. And this can be done manually looking at the curve, precision recall curve that we saw earlier, but also it can be done by approaches of optimization that are meant to give more weight or importance to either precision or recall. And this is actually what I anticipated, what I mentioned earlier. If we have a value of precision and recall that we want to optimize, and we give a first shot of creation of a model from the training, we would be in this position with a default threshold of 0.5. But if we change the threshold towards values that are higher, we might be able to obtain a value of recall that is actually higher. Or if we decrease the value of the threshold, we would be able to obtain a value of recall of precision that is closer to 1. Said that, I want to make understand then that we are not really at the scenario that was described by Professor Dickman yet. In fact, the role of the operator is still central, and we still have the capability of optimize such parameters. This is an element, a requirement that is described on different levels and also by the European Commission, aiming at explainable artificial intelligence and artificial intelligence that can be understood and optimized by the operator. So we have a lot of potential of artificial intelligence and machine learning, and the operator, however, has still a big role in its use as from my perspective at least, or from a perspective of an engineer that is putting into practice such tools, the role of the human, the centrality of the human is still untouched. These last two slides show the potential of such approaches and different versions of it, but we don't have further time to discuss. And I thank you for your attention.
Thank you, sir. Thank you, sir, for this nice and very interesting talk. So, sir, we have received several questions in the chat box. So, I am taking one by one, sir.
Thank
Sir,
you.
the first question is, sir, can we blindly trust the machine learning prediction tools?
Well, my whole presentation said said that we cannot blindly trust, and the role of the human is still central. And for this reason, the optimization that I showed is important. So the answer is, at the moment, no, not yet.
Yes, sir. Yes, sir. And the second question is, sir, what are the parameters that we can use for training the neural network? Is the prediction made using single parameter or multiple parameter?
There are many parameters actually. I have considered just a few, but also I've considered the few that are the most understandable and direct from a perspective of a chemical engineer. So if we have an IT expert would tell us that we could trick and optimize many of them. One that is pretty understandable is the decision threshold, and these can allow us to optimize some metrics such as recall and precision.
Yes, sir. Yes, sir. Thank you, sir. Now, the next question is that which is the faster between multiple linear regression and deep neural network in case of big data analytics?
Well, the faster is multiple linear regression because it's an easier approach. It's less articulated. However, it has limitations. It's more approximative, I would say.
Yes, sir. Yes, sir. And so another question is that in basically in safety domain, sometimes some portion of data follow some distribution, and some portion of data basically rare event. So if we want collectively, if we want to use some machine learning algorithm, then what is your suggestion, sir?
I don't think I understood this last question. Can you repeat?
Yes, sir. Suppose a total safety data set if we use, so the some portion of the data set follow some pattern, but some portion of data set may be the rare event. They don't follow any pattern. Now, if I want to use a single machine learning algorithm which can predict the total data set as a whole, because based on your slide, we have seen that you are telling that some portion of data, when it is a rare event data, so some algorithm are there. Yes, sir.
We shouldn't focus on some metrics like accuracy, but we should better look at recall, for example, in this case. And in this case, we would accept some false positive because it might be that we get some false positive, but we are conservative and we try to consider predict the major events, the rare events. So the answer is optimizing recall.
Mm-hmm. Yes, sir. Yes, sir. Yes. Thank you, sir. And another question, sir, that is coming in our mind that mostly this ML algorithm depends on the data. So how to choose this ML algorithm based on different data sets? Like in safety, sir, we can get different data set from different safety programs.
This is a good question, and I'm not sure I have a clear answer, but based on the purpose that I want to, based on the purpose of my analysis, we might have a hint of the for choosing such algorithms. For example, if we are looking at rare events, if we are trying to predict rare events, we might have a hint of what to use. If we are dealing with highly reliable data, we might be able to use more sophisticated approaches like deep neural network. So another aspect that might be useful to consider is the quality of data. But again, there is not such a thing as a free lunch, and sometimes we get some surprises. So not sure I can fully answer the question.
Yes, sir. Thank you, sir. Thank you, sir, for your enlightenment answer. Now I would like to invite Professor Menon to provide vote of thanks to our expert speaker. Over to you, sir.
Yeah, thank you, Mr. Shomik. So today I'm very the members of CoE-SEA are very grateful to Professor Nicola Paltrineri for delivering this very interesting and important lecture. And I'm very much sure that all our research scholars and our dear participants have benefited from this lecture today. So on behalf of CoE-SEA, I extend my sincere thanks to Dr. Nicola for readily accepting our invitation and to deliver this lecture and being here with us today this evening, even between his very busy schedule. So thank you very much, sir, and we look forward to have more academic collaborations with you in the future. And thank you very much. Thank you. And I also extend my sincere thanks to all our dear participants and the moderators who was present here, patiently listening to this wonderful lecture today. So thank you very much. Thank you to all. So we will meet again next week, the same time, with another expert lecture. So thank you very much. Have a very nice day. Thank you.
Thank you, sir. Thank you, sir.